When military forces tape aluminum foil and metal strips to their combat drones, they are purposefully ruining the aircraft's stealth. Rather than hiding from detection, these materials act like mirrors for radar, effectively shining a spotlight on the drone's exact location in the sky. This deliberate exposure solves a severe battlefield problem. Currently, skies are flooded with swarming enemy strike and reconnaissance drones, like the Shahed and Gerbera. To hunt them down, defensive units deploy tiny, manually flown interceptor drones. Finding a small, fast-moving target in pitch-black conditions is incredibly difficult for a pilot relying solely on a video feed. To meet this threat, a vast ecosystem of purpose-built interceptors has emerged. The Bagnet and its variant, the Alta Ares X-Wing, the high-speed Skyfall P-1 Sun, the joint UK-Ukrainian Octopus 100, the large Odin Win-Hit quadcopter, the fixed-wing VB-140 Flamingo, and the twin-motor Titan. Because many of these interceptors, like the Sting, the AS-3 Surveyor, and the Russian Sokol-E, are rapidly manufactured using 3D printed bodies, soldiers modify them in the field. They wrap the frames in fiberglass reinforced tape, standard for securing small lithium battery management systems, and attach crude metal strips directly to the exterior. These crude metallic additions significantly increase the drone's radar cross-section. Local, friendly radar operators can now clearly track the interceptor on their screens. They use this enhanced signature to guide the pilot via radio, steering them close enough to the enemy target that the pilot can finally take over and engage using onboard thermal or daylight cameras. Deliberately reflecting signals to stay visible is a highly specific tactical anomaly. Usually, engineers employ the exact same materials to do the exact opposite, hiding sensitive electronics by manipulating the physics of the invisible electromagnetic spectrum. Long before it was used to catch radar on a drone, aluminum foil was commonly used to create a makeshift Faraday cage, a physical barrier designed to completely block incoming radio and GPS signals. This diagram shows how that shielding process actually works. When an incoming electromagnetic wave, like a GPS or 5G signal, hits a highly conductive material like aluminum, the wave's energy interacts with the surface. This interaction causes the electrons in the metal to move, inducing an electrical current across the foil. As those electrons flow, they generate their own new electromagnetic field. This newly created field directly opposes the incoming signal, reflecting the radio energy outward and away from the device hidden inside. This physical reflection is known as passive shielding. The metal simply acts as a wall. That is entirely different from active jamming, a highly illegal practice where a device intentionally broadcasts loud radio noise to overpower and disrupt satellite signals in the surrounding area. While wrapping a device in foil creates a perfect shield in theory, it almost always fails in practice. Aluminum oxidizes rapidly when exposed to air. This creates a microscopic insulating layer on the surface. Simply folding two pieces of foil together does not create the tight electrical seal required to properly stop an electromagnetic wave. Without a perfect seal, any physical movement, vibration, or bending creates tiny seams in the foil. In electrical engineering, these gaps act as slot antennas, actual pathways that invite radio signals to leak straight through the barrier. High-frequency signals, like 5G, have extremely short wavelengths, measuring just a few inches. A tear or fold in the foil only needs to be a fraction of that size for the signal's energy to pass freely into the interior space. Because modern GPS receivers use trilateration and constantly hunt for multiple satellite connections, a single leaked signal through a tiny gap is often enough for the device to reconnect. This is why attempting to foil wrap an ankle monitor or a fleet tracker rarely works. The system instantly logs the interrupted connection, and the moment a signal leaks through a gap, a tamper alert is triggered. For large unmanned aerial vehicles, passive shielding requires far more than a layer of foil. UAVs operate in a dense, chaotic environment of electromagnetic interference, or EMI, constantly flying through high-intensity emissions from telecommunications towers, satellite links, and ground radar. Simultaneously, the drone is bombarding itself with internal electronic noise. Components like electronic speed controllers and the rapidly switching currents inside the copper wire coils of brushless monitors generate intense interference, right next to the drone's own flight control units. Onboard wireless power transfer systems, like those found on the DJI F550, generate kilohertz frequency magnetic fields. These fields easily penetrate standard non-metallic drone chassis, causing severe disruptions to the sensitive telemetry and navigation electronics inside. To survive this crossfire, engineers utilize specialized materials. Companies like TE Connectivity design lightweight conductive enclosures to protect components, while agricultural drones rely on heavy-duty Raychem tubing to shield their cables and ensure their GNSS data remains uncorrupted by onboard power systems. Tactical reconnaissance and urban delivery drones require flexible seals for their avionic bays and access panels. They use metal meshes, plated elastomers, and slow-oxidizing beryllium copper EMI gaskets to ensure every mating surface is electrically continuous. True EMI shielding requires engineering a perfectly sealed, oxidation-resistant ecosystem capable of neutralizing both the noise the aircraft flies through and the noise it generates itself. All of those shielding techniques apply to the drone's internal computers. But there is one area of an aircraft where conductive shielding is impossible, exposing it to the most extreme electromagnetic threat in aviation, a direct lightning strike. This electrostatic field diagram illustrates the problem. Radar and satellite communications antennas must sit behind protective radomes. Because these antennas cannot operate if enclosed in metal, radomes are built from dielectric, non-conductive materials. As the red zone in this model shows, the radome offers absolutely no electromagnetic screening, leaving the metallic antenna inside as a massive electrical stress raiser and a prime target for lightning. Historically, engineers protected these areas using solid diverter strips. These are thick, solid metal bars fastened directly to the outside of the radome structure with screws, acting as traditional lightning rods to catch the strike. Solid strips are highly durable and can take multiple direct strikes, making them standard for commercial weather radars. However, that large mass of solid metal physically blocks radio waves, heavily interfering with the radiation pattern of the very antenna it is trying to protect. Looking at this cross-section diagram, we can see the modern alternative, segmented diverter strips. Instead of a solid bar, these strips consist of a series of tiny, closely spaced conductive buttons adhered to the radome surface, typically measuring between 0.76 and 1.52 millimeters in diameter. Because the buttons are so small, they are nearly transparent to the radar signal. When the extreme electric field of an impending lightning strike approaches, it ionizes the air directly over the gaps between the buttons. This creates a continuous, highly conductive plasma channel hovering just above the strip, which safely guides the millions of volts of lightning across the radome surface. Determining exactly how far apart to space those buttons requires rigorous testing, especially for hybrid protection systems on medium-altitude long-endurance UAVs like the Tellurian. Engineers place the radome's A-sandwich core structure beneath cowering high-voltage impulse generators, hammering the composite panels with specific electrical loads, known as waveforms A, B, and D under IEC and EB84 standards, to locate the exact breakdown voltage of the material. The resulting protection system relies on exact mathematics and material science. To keep a radar system alive in a storm, engineers must literally harness and guide plasma across the skin of the aircraft. The electromagnetic spectrum dictates what survives in the air. On one end, you have troops using household tape and foil to manually guide 3D printed interceptors through the night. On the other, aerospace engineers are calculating the precise ionization voltages required to slide lightning over a radome without blinding the sensors inside. As unmanned systems continue to saturate the airspace, payload capacity and top speed are no longer the only metrics of a successful aircraft. The defining feature of modern flight is total mastery over invisible energy, learning exactly when to perfectly shield a signal and exactly when to reflect it. How do you see field-expedient DIY modifications continuing to impact the design of highly engineered military systems? Let us know your thoughts in the comments below. And as always, remember to like, share, and subscribe for more deep dives into the engineering that shapes our world.